Hello everyone, I'm Gregory Moille from UMD and NIST, and today I'm gonna present you our work on synthetic dissipative Kerr Soliton photonics molecule. So let's start with the idea of coupling, right? And a lot of systems are actually based on energy exchange between different systems. And that is the core of a lot of experiments, which can be actually quantum or optics. And why actually a lot of optics? Because optics share the same waveform rhythms and quantum mechanics. So it's actually a great tool to emulate a lot of systems that actually either are to experimentally demonstrate in a quantum way or just easier to fabricate. And that, for instance, true for like PT symmetry. PT symmetry, because it involves losses, it's very hard to actually get in a pure quantum system or in optics. We deal with loss all the time. But also we have systems like topology actually that are very, very easy to, that are convenient to fabricate in optics with like a couple of resonators. But all these systems actually rely on linear coupling. That means you take two resonators together and you bring them. And that's mean like only resonance that are the same momentum and same energy will actually couple together. And that's a fundamental limitation of linear coupling. But we know that we have nonlinear effect, and nonlinear effect can actually allow for coupling between modes that are actually not at the same frequency and not the same momentum. And so we can, for instance, use only one single resonator, like a ring resonator that is multimoded, to actually couple frequencies that are in different mode numbers. But in addition of like coupling, actually, we create new light at new frequency. And frequency comb are one of the main examples of that. And that's really push actually the creation of new frequency at kind of at its maximum, because we have this whole cascaded process that creates this whole comb. And what is interesting with the frequency comb is that we actually create a nonlinear all-to-all coupling. And that's very well seen actually in the master equation that we use to model comb, which is early because it's actually a single wave packet. We don't work in the mode domain, we work actually in the resonator angle. And that's a single equation that only takes into account the self phase modulation of this wave packet. And recently there is a lot of work actually that has been done in a copper resonator under DKS operation. There's really interesting work by Professor Kippenberg's group, for instance, on photonics molecules that show emerging phenomena with creation of new dispersive wave, where we have the coupling and different DKS and PT symmetry. And you also have topological DKS that has been recently demonstrated theoretically by a collaboration at UMD. But still, even if you create DKS that are fundamentally nonlinear, you actually rely on the linear coupling between resonator. And so that means you are fundamentally limited. So can you actually nonlinearly couple dissipative Kerr Soliton? And could you actually go beyond the limitation of linear photonic molecule? And for that, for instance, you take one resonator, you multi-pump it or whatever, and you can actually create coupling between the different wave packets. So instead of having one soliton, you could actually have multiple soliton, for instance, and you couple them together. And that have actually been recently studied in some very interesting work. For instance, this work also by Professor Kippenberg, where like theoretically they show coupling between different modes, actually creation of what is called Venn soliton. And Nicola presented you earlier, like this block oscillation is very, very interesting work on block oscillation and dissipative Kerr Soliton. But most of this work actually rely on electro-optics modulation. It's a nonlinear phenomenon, it's a Chi2 phenomena, but the issue is that it's low FSR. You cannot go to this kind of 1/3 repetition rate that we actually use because we care about octave spanning comb. So can you actually use something that doesn't care about repetition rate? And for that, you can use for mixing, for nonlinear coupling. So the impact is that it has a pure optical coupling. You can use whatever repetition rate you want as long as you can match frequency and mode matching for pure K3 stuff. But to do that, we need to use multiple driving force. That means you need to have different pumps. And actually, that's been shown in waveguide, for instance, by Professor Eggleton, where they do synthetic frequency lattices using Brascaling. So as I said, like you need to have pure optical nonlinear coupling to use this large FSR, and you need to inject multiple driving force. The thing is actually multi-pumping, especially dual pumping, has been quite studied in the past few years. Actually, I've shown nice stuff. For instance, like this theoretical work by Professor Scriabin on soliton blockade. You also have soliton crystal creation. You have discrete temporal time crystal by Hossein, which is an amazing work. You have bright and dark soliton molecule, and you also have single path dispersive wave creation to nonlinear scattering of a soliton. And we have shown recently that you can actually have spectral extension on both sides of the spectrum, and I will emphasize on that really on both sides. That means it's very important. It's actually like one of the fundamental starting point of what I'm going to present you today. But actually, what happened is when you think about the spectral translation, that could be like the single pass, or the, like in this work by the Newton group, or spectral translation on both sides, you actually have frequency offset. So that means you do not have a single big frequency comb, but instead you have different wave packets that are frequency offset, so phase shift between each of them. And actually, we've shown that in our previous work, where we actually have 3 wave packets. So we have like the high frequency, the primary DKS, and the other one that is secondary pump. And actually, there is a frequency shift, frequency offset between each of them, while they actually travel at the same repetition rate. So the question here, and I will try to answer and show you how actually this is interesting, is that can we explain this frequency offset? But most importantly, can we harness it? And can we do something with it? So I'm going to go through a bit of theory, and I'm sorry about that. It's a slide just with equations. There's actually no graphic, but it's short. It's actually needed. So first of all, let's start with the early underdual pumping. So most of the people here know probably is like regular early. So you have the dispersion here. It's actually an operator just to make it easier with the integrity dispersion. You have the nonlinearity. And interestingly, you have the second pump with that actually a mode shift, because you pump at a different mode that your primary pump, but also you have a phase shift, because you have the integrity dispersion and it's an external force. You have to be on resonance. So it's not on the spectral grid of the DKS, which is a fixed spectral grid, which is different from the grid where there is a dispersion of the resonator. So if you do the Fourier transform of this equation in the mu domain, you retrieve the regular couple mode theory that everybody knows. But the point is that there's another dimension. There's this phase shift dimension all of a sudden, right? So you could do a Fourier transform in this domain instead. So if you do that, well, same thing, you retrieve a couple mode theory, not in mu, but instead in the domain defined by a repetition rate omega here, which is actually the integrity dispersion at the secondary pump, plus the frequency shift of the frequency detuning of the secondary pump, with the sum of all the nonlinearity possible. And all of a sudden, you remove actually the phase shift here on this pump, because you take it into account in this Fourier decomposition. And experimentally, what we have shown is like there's only 3 waves that we can take into account. And you end up with this kind of system that actually end up being an OPA. What is very interesting is like in this term here, you will find surface modulation, cross modulation, very regular. But interestingly, in these 3 terms, you end up seeing the coupling. And that's the same coupling as you would have in an OPA in an OPO system, which means that effectively we have 3 wave packet, minus, 0, plus, where we pump the minus and the 0 wave packet. And each of them are coupled to one another through a nonlinear coupling. And that's really what is happening, is we have a nonlinear coupling between 3 wave packets. So here I'm going to try to demonstrate to you experimentally this theory. So to do that, we use a 1 terahertz ring resonator that we send a cooler pump at 980 to thermally stabilize the system to actually create the DKS pump at 1060. And we have a lot of other lasers to access all the different modes possible. So we use the same exact Dissipative Kerr Soliton that we pump at 1060, as we say, and we actually extract the experimental integrity dispersion that match very well with FEM simulation. And then we pump, we send a secondary pump, and I expected we actually get a new dispersive wave where the band actually of the dispersion of this wave packet cross 0. Here we do not see actually the idler, although it exists. It's just because we have very poor outcoupling and we cannot see actually the resonance interaction. But if you change your mode, if you actually swap your sign of omega, what happens is you inject your secondary pump here. That means your minus band become up there and the plus band become up there. And actually you would have a resonance enhancement in spectral region that you can actually effectively extract. So through this way, we can actually show both the signal and the idler wave packets. We do that for all the modes possible. So for instance, in the 1300 band, so on this side of the integrity dispersion, where we would see the resonance element on the other side, we do it in the 1400 band and the 1500 band that allow you actually to retrieve the idler wave packet that obviously has a lot of mu components. We can focus on the dispersive wave of the primary DKS that has actually a fixed wavelength. This one doesn't change. And we can actually record the frequency overlap between the different the signal wave packets, the one that is actually secondary band. And we can clearly see that this omega is changing, but what we can do even more is like extract the envelope of each wave packet and plot them in this integrity dispersion phase space. And what we can see is, first of all, it match actually the integrity dispersion, which means that they do the primary DKS and the other wave packet don't have a different slope. That means they are actually at the same repetition rate. And what we can also see is that the phase matching is actually true. So that means we have an OPS system because we only have a change of sign between the omega, between the signal wave packet here and the idler wave packet. So, okay, great. We have a spectral transition and resonance element when the integrity dispersion cross 0. But what are actually these wave packets? What is the nature of this wave packet? And so this is way to explore actually removing the resonance enhancement. It's actually fairly easy because like every time we cross the integrity dispersion, we have resonance enhancement, but because we can play actually with the detuning of the secondary band, we can actually go beyond the maximum of the integrity dispersion. That's actually been shown in this paper by Stuart Murdoch group, where the detuning is very important. So for instance, if we focus here with a large detuning, experimentally, we can see that we do not have any resonance enhancement, and actually through the area, we can clearly see that's become a dark force. Interestingly speaking, we do not pump at the group velocity matching. We actually pump over there. It's only the detuning that allow you to not have any resonance enhancement. If we bring the detuning closer and the idler, the single wave packet closer to the integrity dispersion, we start to see actually this dispersive wave enhancement, and then closer and closer. And then when we actually be on resonance with the detuning equals 0, you still see this kind of dark pulse, but the integrity dispersion is taking over, the dispersive wave is taking over, and that's why we have this modulation. But essentially, we always have basically a dark bright pulse. Only the dispersive wave takes over the modulation. What is interesting is that we can actually get what that kind of tells you what happened at the idler wave packet. That means we can also have like a dark pulse translate far, far, far away in the mu domain on the other side of the comp. And that's consistent actually with the literature, and that actually these wave packets are binded because that's the same as what has been shown by Stuart Murdoch and Miro Quintalo about this Kirby sideband type of system. So the question is that in synthetic frequency lattices, they've shown that you can have complex sound range using different repetition rates. Can we actually do the same stuff in our system? And so we can reproduce through multi-pumping. For instance, if you pump 1, you pump 2, you get the same stuff that we had before. But if you inject 2 pump, actually, you will have like the interaction between the different levels. But you will actually create new levels from scattering between the interaction of the different secondary pump from the primary DKS. And what is interesting, it's allow for cascaded process. And that's why you can really think of that as a synthetic dimension, is because you will be able to have that cascaded process. And if you inject the third pump, you create that. But if you start plotting actually in a better way, in a vertex and graph way, this coupling, you can really see that you have created a synthetic DKS photonic molecule where different coupling are allowed or not. And because you actually have forbidden coupling, you can actually have analogous with atomic state. So in conclusion, we have proposed a theoretical model for dual pump DKS, resulting in OPA-like process in synthetic dimension, experimental demonstration of the validity of the model, complex synthetic DKS photonic molecule under multi-pumping. And what does that mean? That means we have introduced a pure optical synthetic dimension for under DKS. And that kind of create new topology in the phase slip dimension, so this FCU or the frequency mismatch. And hopefully we hope that it allows for new possibility to harness high dimensionality of DKS in this graph. And I would like to thank everybody who worked in that. So Karlik and Edgar, Jan, who worked with at UMD, and Curtis Menuik, that is at UMBC. And with that, if you have any questions, please feel free to reach out, and hopefully we will have an archive soon to show you. Thank you very much.